Let's get started. Good afternoon and welcome everyone to the Simons Institute Breakthrough Lecture, which today will be on strong bounds for three progressions by Raghu Meka. So my name is Venkat Guruswamy and I'm a senior scientist here at the Simons Institute. First, a brief blurb about the Simons Institute, because this is a talk which is streamed and for those who may not be familiar, the Simons Institute is the leading international venue for collaborative research in theory of computing. It was established in 2012 with a generous grant from the Simons Foundation, who also continue to support the Institute in very generous and various ways. And the Institute brings together the world's leading researchers in theoretical computer science and related fields, as well as the next generation of outstanding young scholars. And this is the 10th year of actual programs at the Simons Institute. And we're really proud of the achievements of the programs, which have pushed the frontiers of TCS in so many directions. They have resolved many long-standing open problems and also have opened up new lines of inquiry and lots of connections with other fields. So in addition to hosting thematic semester programs as its principal focus, the Simons Institute also conceives and hosts various outreach activities to share the exciting developments in the field with the TCS research community at large, as well as the general public. And today we have a lecture as part of the Institute's Breakthrough series, which showcases exciting breakthroughs in the theory of computing or related fields to the scientific community. Today's Breakthroughs lecture is about remarkable progress on a very old problem in combinatorial mathematics and number theory. How many numbers can one pick while avoiding three of them lining up in a sequence in an arithmetic progression? And it's yet another compelling illustration of how theory of computing is intertwined with mathematics and enables surprising progress in math as well. And this breakthrough is by Zander Kelley and Raghu Meka, and our speaker today is Raghu Meka, who I'll briefly introduce now. So Raghu is a faculty member in computer science at the University of California, Los Angeles. He received his PhD from UT Austin in 2011. And after that, he was a postdoc at the IAS in Princeton and at DIMAX in Rutgers. And after that, he had a stint as a researcher at Microsoft Research in Silicon Valley, and before moving to his current position at UCLA. He also spent extended time at MIT recently on a sabbatical, and he has amazingly broad interests in the foundations of computer science, particularly algorithm design, complexity theory, pseudo-randomness, and machine learning lately. And his findings on three progressions are only one of his many notable accomplishments in a diverse range of topics. And so before I hand over the floor to him, just a reminder that this is a hybrid event. So just for people in the room to ask questions, just raise your hand. We'll try to pass the mic to you. And I will also be monitoring the Q&A on the Zoom channel. And so if there are questions there, I'll pass them on to Raghu, or depending on, sometimes I might just decide to batch process them towards the end. So we will make that call. So, and last thing I wanted to say is that we have the official part of the talk is a 1 hour thing. And after that, what Raghu has kindly agreed to do is a bit of a deep dive into any technical aspects which people might be interested in for about half an hour afterwards. And that part will not be, will just be for the in-person audience and would not be recorded. Okay. So with that, please join me in welcoming Raghu.
Thanks, Venkat. That'd be very kind. And today I'll tell you about this new work on finding arithmetic progressions in large subsets of integers, and this is based on joint progression. So this is based on joint work with Zander Kelley from UCLA. So the problem that we study is due to Erudit and Turan, who asked in 1936, who asked the following question. Suppose you have a subset of integers. All we know about the subset of integers from 1 through n is that it has many elements. And throughout this talk, I'll use, I refer to the density of the set as its size relative to the universe. So what fraction of elements does it contain? And here I'm denoting it by delta. So the question they asked is, how small can this density be while always guaranteeing that you'll find 3 numbers which are equally spaced, or 3 numbers in an arithmetic progression. And for the rest of the talk, I'll just say 3AP for short for 3-term arithmetic progression. And so almost immediately after Erudition-Turan posed this question, Behrend gave an example saying that you cannot get really, really good results here, in the sense that there exist sets of density roughly 2 to the minus square root log n, which do not contain any 3 numbers in a sequence. And this is a beautiful geometric construction, which also has applications, surprisingly, to some communication protocols that I'll talk about in the very end of the talk. And since then, there's also been a lot of work on the problem, particularly with the seminal work of, starting with the seminal work of Roth from 1953. We showed that you do indeed start finding arithmetic progressions as soon as the density is at least 1 over log-n. So as long as you have some fraction of elements, you're going to find 3 numbers in a sequence. And this was exponentially improved by Heath, Brown, and Samaretti, who improved the density. So the main question is how small the density. So we're always kind of slowly improving the density in the sequence of works. I'm also skipping many works here. There's a rich history on this problem. It's almost 70 years old. I'm only kind of covering the things which are important when showing up in the rest of the talk. So Bourgain in 1999 and 08 introduced an important technique called Bohr sets, which we also use, and also improved the density bound that you require to find 3-term arithmetic progressions. And Sanders in 2011 kind of got close to 1 over logarithmic density. And this is something that will play a role later on in our work as well. But for many of these older techniques, it seemed like 1 over log was a barrier that you couldn't overcome, but it was overcome in a very nice work due to Bloom and Sisask, who showed that even if your set is small enough that its density is only 1 over log n to 1.01. So you're slightly worse off than logarithmic density by small constant in the exponent. Even then, you're going to find 3-term arithmetic progressions. And the 1 plus c might not seem that significant, but was actually very significant because it gave the first progress on another Erudish problem in number theory, which I don't have time to discuss today. And what we show in this work is the true answer must actually be closer to Behrend's construction from 1946. That even for quasi-polynomially small sets, you are going to start finding our 3-term arithmetic progressions. I'm using the term quasi-polynomial in a loose sense here. Don't argue with me about it, but basically density, which is 2 to the minus log n to the small exponent on top of that. Okay. So you're getting closer to Behrend's answer than to the previous constructions. So this is the main result. And before saying a little bit more about it, let me take a detour. I should also say that we don't just say that, unlike like most of these works, we don't just say that there is a single 3-term arithmetic progression. Once you find one, you also find many, many 3-term arithmetic progressions. Okay. So you get almost a quadratic number of 3-term arithmetic progressions as long as your density is not too small. Let's take a detour to finite fields, and I'll tell you why in a little bit. So the question that we're studying can be understood as follows. You have a subset of integers a, 1 through n, of size delta times n. And what we want are 3 distinct numbers a, b, and c from the same set, which satisfy the equation a plus b is 2 times c. If a plus b is 2 times c, then they form an arithmetic progression, and that's what we're looking for. And we can also ask for a similar question, not just over integers, but also over other groups, or in this case, even just finite fields. So now I have some finite field fq to the n, and I have a subset a of integers of fq to the n. The density is still delta. And we're looking for the same thing as before. We want 3 unequal elements, a, b, c, from your set A, which satisfy the equation a plus b is 2c. I mean, usually integers are harder than finite fields. Finite fields are an easier space to work with. And here also something similar happens. And in fact, something drastic happens. What do I mean? Behrend's lower bound construction no longer works. What Behrend showed was that there was an AP-free set of density roughly 2 to the minus square root log n. That construction does not work over finite fields. And it doesn't work for a good reason. In 2017, a couple of papers in a breakthrough showed that even exponentially small sets must have 3-term arithmetic progressions over finite fields. So even if your density is exponentially small compared to the size of the universe, you must find 3-term arithmetic progressions. And the case where the field Q is F3, it's called the cap set problem. And that's what I'm going to focus on for the rest of the talk too, just for clarity. It doesn't change any of the math or any of the conceptual difficulties and techniques that we are going to see. Okay, so just think of F3 to the n. You have a subset. I want to find 3 elements from the set which are satisfy the equation a plus b equals to c, and we are good. So this work, which shows that exponentially small sets must also satisfy, must also have 3-term arithmetic progressions, use a beautiful algebraic technique. The proof was by the polynomial method, and it doesn't quite carry to integers. And it shouldn't, right? Because we know that you cannot get such exponentially good bounds over integers. But on the other hand, the previous methods of Roth, Heathburn and Semeredy, Bourgain, Sanders, Bloom and Sisask, and so on, they all use analytic techniques to prove the statement that they show. Analytic meaning they use Fourier analysis and all of those things. And these methods can be pushed to integers. In fact, and often a commonly seen theme across these works is you first work over finite fields, maybe for exposition or for clarity, and then kind of translate the arguments to integers. Okay. And that's actually what we also do. So we give an analytic proof that subsets of density, quasi-polynomially small density, must also have 3-term arithmetic progressions. And this is our finite fields. As stated, this result is much weaker than what we know our finite fields. But the point is that we are going to use analytic methods, which we can then push to integers, right? And translating it to integers actually is a lot of work, but it involves many other techniques which have been developed. But today I'm only going to focus on the finite field case. And subsequent to our work, Bloom and Sisask in a follow-up gave a much cleaner way to translate our arguments from finite fields to integers. And along the way, also got some new improvements for many other questions. Right. Okay, so rest of the talk, the setup is as follows. We just have a subset A of fq to the n. Think again, q equals 3, f3 to the n. Density is delta. And we want 3 unequal elements a, b, c, which satisfy the equation a plus b is 2c. The proof has 3 ingredients. The first ingredient is really the bread and butter in this area and additive combinatorics in general, which is structure versus randomness. All right. And in fact, I would say one of the most important reasons for studying the 3AP problem is that it's been kind of the originator of many techniques which have had many other applications, not just in additive combinatorics, but also within TCS. Like structure versus randomness, this dichotomy, and so on, have many other applications. Okay, so that's the first step. The second part is kind of new to our work, which I'll call spectral positivity. And I'll tell you what that means and how we use it later on. The final ingredient is a technique we call sifting for finding additive substructures by using some kind of algorithmic tool. Let me start by describing the standard approach that standard paradigm of structure versus randomness for finding 3-term arithmetic progressions. Okay. Okay. So what is the structure versus randomness? It's really just a win-win wishful argument. So what's a wishful argument? So let's suppose as a thought experiment that you pick your set A completely at random. all we knew to begin with was the set had certain size. That was the only constraint. But let's say you were just picking the set to have density delta and at random. How many 3-term arithmetic progressions would you expect in such a set? How many solutions to the equation a plus b equals 2c would you expect if the set A was random? Well, there are n squared such triples. Once I know A and B, this third choice is fixed. So there are capital N squared many such triples. And each triple is has delta cubed chance to be in your set A. Right? Each of them is being chosen independently. We're just doing a thought experiment. If you're very lucky, the number of solutions to your equation in A should be delta cubed times n squared. That is if your set A is completely at random. And if this is much more than the number of trivial solutions, then you must have many good arithmetic progressions. Okay. So the win case one for structure versus randomness is maybe this heuristic argument can be made to work, even if my set is close to uniform in some sense. Okay. So you want some notion of closeness to uniform, which will tell us that, okay, if you're close to uniform in some sense, then you get many 3 APs. Okay, so that's the win one product. Well, not all sets must be close to uniform. What do you do if you're not close to uniform? That's the second thing that we need. If you're not close to uniform, but your set looks something like this, you would like to say that you can identify some structure in this set. I don't know if anyone can see the structure here yet, but if your distribution A, the uniform distribution A is far from uniform, then we want to say that some structure arises within it, and we make some progress, whatever that progress is. In particular, in the picture that I showed, if you look at it at a certain angle, all the points lie in this small affine space. Okay, we drew a plane, all the points were in that plane. And that's the ideal scenario for us. Either you're close to uniform, in which case we're already done. Otherwise, there is some subspace V on which you have more elements than you should have to begin with on average. Okay? So there's some subspace V where the size of A restricted to V is more than delta times the size of the overall ambient space. So you have a density increment. If this is the case, then we made some progress in the sense that I can focus on just the space V. And this is the beauty of finite fields, why everything is kind of nicer over finite fields. Once I move to the subspace V, it's as if I'm starting with the same question again. So everything is isomorphic. So you can just do, it's as if I'm just working with F3 again, but over a smaller dimensional space, but I'm starting with a higher density. Okay. But of course, as stated, I can then do induction on V or just recurse on V and keep doing this. But as stated, this would be a silly thing to hope for because I can just say, okay, here's my single point in A, is a subspace of dimension V, and I have density increment 1. So it's meaningful. We also need to look for a subspace V, which is big. Okay, you can't just say there's some small subspace on which you have many elements. You want to say that there is a large space where you have more elements than you should have started to begin with. So largeness of a subspace for us will be measured in terms of the codimension. Codimension is just saying how many extra constraints are you placing on your subspace. So it's n minus the overall dimension of the subspace. Okay. So that's the template. And let's go back to Roth's original argument. Let's just do a quick walkthrough of what Roth did, and then we'll try and modify it to see to get the new bounds. And this is based on the Roth, this is called the Roth-Meshulam argument, and it goes as follows. So what is the notion of closeness that they studied? So again, as I said, you have A, which is F3 to the n. They said if the set A is almost random in the sense that it is small biased, it's something that we all study in theoretical computer science, then it has many 3 APs. Small bias just means that the uniform distribution on the set A looks random to simple linear tests. So in particular, if I pick X uniformly at random from A and add up the elements or add up the coordinates of X, it takes the value 0 with probability roughly 1/3. It takes the value 1 with probability roughly 1/3. 2 with probability 1/3. There's some error delta, but as long as this error is like a constant factor worse than delta, you do get many 3-term arithmetic progressions. Yeah, that's wish 1. Closeness is defined by whether or not you full linear test, and if you full linear test, you do get many 3 APs. The part 2 is if you're not small bias, then almost by definition, there is a linear test which is telling your set apart from a uniformly random distribution, and that gives you a density increment. So you can find an affine space, in fact, codimension 1, onto which you increase the density, but the density increment is somewhat small. You started out with density delta. You started out with something which has delta fraction of elements. Now you have delta plus delta squared. A slight improvement, but not, it's something. And so the template then is, you started out with the original set A, and your whole space F3 to the n. You have delta fraction of elements. If you have APs, then you're good. If you don't have any APs, then you must have density increment onto a subspace of codimension 1. So you went from delta to delta plus delta squared, reduce the dimension by 1. If you have APs, you're done. Otherwise, do the same thing again. It becomes 2 delta squared, keep repeating. If you do this 1 over delta iterations, then it's your density increases by some constant factor. And you can now do some other stuff to get a contradiction, because density cannot ever be more than 1. Okay. And the limit to this argument is that each time you do it, you're adding 1 extra constraint. Your codimension is 1. You cannot ever add more than n constraints. So this argument works as long as the density is 1 over n. So as a sketch, we just saw the proof of this theorem, this finite field version of Roth's argument. If I have a subset of F3 to the n, and it has 1 over n fraction of elements, then it has many 3 APs within it. So this is a template that we're going to start with. This is structure versus randomness 101. Where do we go from here? How can we go beyond? So there are 2 ingredients here. One was defining this notion of closeness to uniform, which allowed us to immediately say you have many 3 APs. And then the second part in the Roth-Mechoulam argument was how small a subspace do you find? How large a subspace can you find before your density becomes larger by a constant factor? In the old argument, you had to do it many steps. You had to go to codimension 1 over delta to increase the density by a constant factor. Can we improve this? In particular, we will be looking for polylog 1 over delta, but you don't have to pay too much attention to the actual parameters. They'll come out more naturally, but just keep this template in mind. All right. Okay, let's focus on the first step. What notion of closeness would be enough? So they use closeness as measured by fooling linear tests, but let's take a minimalist approach. Let's start working backwards from what would actually be enough to guarantee us that you have many 3 APs. To understand that, let's look at our equation again. We have some set A, and we want distinct elements A, B, C, such that A plus B equals 2C. A convenient shorthand that people use in this literature is summing sets. Okay, so meaning A plus A is the set of, you take all pairs, all distinct pairs, and just add them up to get a new set. 2 times A is just you take all elements in the set A and multiply them by 2. With this new notation, what we want becomes this equation. We want to say that A plus A intersect 2A is not empty. In fact, we want something more quantitative. We want to say that this intersection is big in some sense. In what sense? Should we just count the number of elements in this intersection? Not quite. That's not the right thing to do, because when you look at the sum set A plus A, some elements might be representable in many different ways as sum of 2 things, or something might have a unique representation. And if I throw 2 dice, there's only one way to get 2, whereas there are many ways to get the number 7. Okay. So you have to take this counts also into account, but it would be nicer to take that into account. And the right way to quantify it turns out to be the following. Suppose I pick a uniformly random element x from A, and then y is also uniformly random from A, but it's independent. What is the chance that their sum ends up in this set 2 times A? If the chance that the sum ends up in 2 times A is big, then we must have many, many 3A pairs. Okay, because it's giving you many pairs A plus B, which are lying in 2 times A, so you're good. That's the way we are going to quantify what we want. And here I'm putting omega of delta because this is what you would get for a random set. A is a random set. Then the only thing we know about 2 times A is density is delta. So maybe x plus y should land within it with probability delta. Seems too wishful, but let's see what we get if this is what we focus on. But before that, what is the distribution of x plus y? I know the distribution of x, and I take an independent copy y, and I add them up. What distribution do I get? Well, this is probability 101. Here, I actually do random numbers from 1 through 10,000. You get some density with density, I think 0.01 or something. The PDF of x is shown in blue, and the density function, the distribution of x plus y, is shown in magenta. It's much nicer, smoother, kind of flatter, and everything is nicer about the density of x plus y. And we actually have a closed form expression for what the distribution of x plus y is. It's the convolution of the distributions that you started out with. If you have 2 random variables, then the distribution of the sum of them is given by the convolution of the original distributions we started out with. Okay. So if I denote mu a as the density of x, then the density of sum of 2 independent copies is mu a convolved with mu a. And here, just to be clear, I'm using the density notion. The normalization is not very important, but that's one that is easiest to carry around. So we're thinking of the distribution on A being normalized so that instead of adding up to 1, its expectation is 1. And the convolution operation is what you see in probability theory and everywhere else. So F star G is expectation over some random element Z of F and G evaluated at points where they add up to X. And we also look at something called difference convolution, where instead of looking at the sum, you look at the difference of the 2 things. Okay. So what's the expectation of F evaluated at a point and G evaluated at a point where the difference of the 2 is conditioned to be X? In the usual convolution, you take the sum, here you're taking the difference. All right. Okay. So let's keep that in mind, that the distribution of the sum of 2 independent copies is given by the convolution. And let's look back at the condition that we want. We want x plus y, the distribution of x plus y, to kind of be uniform in the sense that it hits the small set A with some noticeable probability. So what is special about this set 2A? Is there something important that the set A is also used in the definition of x and y? Or maybe all we care about it at this point is that it has some number of elements. So you're going to take a leap of faith and just ask for something much stronger. So I'm going to ask that you have x and y drawn independently at random. Then the sum x plus y is almost uniform over the entire space in the sense that any not too small set gets hit the right fraction of the time. If x plus y was indeed uniformly distributed, then the probability that it lands in the set T is exactly delta. And we're saying, okay, I want such a strong condition, not just that it's true for 2A, but for every set T, the chance that you land within it is maybe delta over 10, delta over 2, something, some constant factor. So what does this mean? So let's look at a picture, very caricature caricaturist picture. So the x-axis is all possible elements in the finite field, f3 to the n. And the y-axis, I'm just writing down the chance that x plus y actually takes that value. So it's the density of x plus y. For reference, the truly uniform distribution would always be the constant value, which is the yellow line here. And if this is the heating property that I want, and I show you the density, what would be the worst T to pick? The worst T to pick would be all those things which are where the value is very small. So I look at all possible points where the chance of taking them is small, 0.1. And let me focus on those elements in the universe. If this region has high mass, there are many, many points like this, then I'm in trouble. Then I'm not satisfying the heating property. Okay. So far it's just almost by definition. And here I'm going to actually make that a formal definition and call a density anti-concentrated. I'm calling it delta anti-concentrated here, but forget, as I said, I'll be loose with the parameters delta because we're just going to keep one parameter throughout. If the probability that the density takes a value less than 0.1 is not large. In fact, if it's a uniform distribution, it's always 1. So this probability should be 0. And I'm allowing you some error. So I'm saying you can take the value less than 0.1, but you should not take it more often than delta. Okay, so it's anti-concentrated, meaning you're not going to take a small value with non-negligible probability. All right. And the notion of closeness to uniform is going to be very different from Roth's argument. So they studied just linear tests. And now we're going to say A is close to uniform if the density of A convolved with itself is anti-concentrated. Meaning once I convolve A with itself, you have the heating property. Any big set will be hit. Any not too small set will be hit the right amount of time. And the first lemma, structure versus randomness lemma, would be that if the density of A with convolved with A is anti-concentrated, then we have many 3 APs. And the proof of this, again, as I said, is almost by definition. You say, okay, if it's anti-concentrated, what's the chance that x plus y lands within 2A? There are delta fraction of elements, and at most delta over 2 where you are 0.1. Just do some arithmetic. You get that they're at least the right, almost what you get in a uniformly random set. So to summarize the structure versus randomness part, you have this dichotomy that you're shooting for, win-win analysis. Either you're close to uniform or you get density increment. And the notion of closeness we zeroed in on was that the density of the distribution convolved with itself is anti-concentrated. Okay, so A convolved with itself must be anti-concentrated. And if it's anti-concentrated, then you have many APs. That's kind of wish one. What we have to do is to do the second part, which is where we kind of push all of the difficulty down to the second part to say, if you're not anti-concentrated, then you need to identify some structure. Then you need to find some increment onto a subspace. Okay, so let me try and talk about that. So any questions about the overall paradigm? Okay. If not, let me go on to the second part, which we call spectral positivity, which allows me, sure.
So was this kind of pseudo-randomness part of any previous work, or is this new to your approach?
I think it's implicit, you would say, something like this is implicit in various work. Maybe when you go to spectral positivity, that part is new. Okay, so it's, in some sense, so far we just restated the definition, right? If it's anti-concentrated, then you're good, because you're good for any small set, so in particular for 2 times. But the second part, spectral positivity, will allow us to get a drastically different formulation of this anti-concentration. So again, go back to our picture. What do we want now? So you have something so that the distribution convolved with itself is not anti-concentrated, meaning it's taking small values more often than it should. Okay, so you kind of have this scenario. Well, this seems like a strange thing to study, But what we have studied across many different fields is, okay, I want to say you're close to uniform in absolute sense. So maybe I have the uniform, like the constant one function. I could say you're actually close to the constant one most of the time. That's a better thing to study using various analytic tools. Okay. If I want to do something like this, there are two kinds of errors you see here. Upward errors, meaning values where my function, my density is taking values which are much more than one. And there are downward errors, which is what we actually have, where it's taking too small values too often. Okay, there are two kinds of errors. You can have upward errors, you can have downward errors. And our assumption is that you don't have downward errors. And from that, we want to get to a structure statement. Unfortunately, if you have general densities, you can actually have distributions which only have downward errors with no upward errors. I can have a distribution which looks exactly like this. It never goes too high above 1, but it goes low often. But this is the assumption that we started out with. And for reasons that will become clearer later, we argue that such a thing cannot happen for the specific distributions we study. More generally, we show that for a large class of distributions, you cannot have only downward errors as long as they have this property that we call spectral positivity. So what is spectral positivity? It's just the condition that any distribution or any function has Fourier coefficients. Even if your function is non-negative, its Fourier coefficients need not be non-negative. They can be complex numbers, they can be all out negative numbers, whatever. If you say the function is spectrally positive, if all of its Fourier coefficients are non-negative. They can be 0, but they cannot be negative or complex. Okay. And the condition that we show is that if your distribution is spectrally positive, then you cannot have only downward errors. Meaning if you're going low, you should also actually come up often enough. Okay. And in particular, if you're spectrally positive and not anti-concentrated, then some k norm of your function must be 1.01. The normalization here is that, the definition of k norm is just the expected value of the kth power of the function. But just think of it as saying that you are taking the value 1.001 reasonably often. If you're taking the value less than 0.1 often, then you are taking the value 1.001 also often. Okay, you can't just be lower, you should also go higher. All right. Okay, that sounds good. Nice. If you have spectral positivity, you have this. But why is that relevant for the problem that we started out with? Well, we kind of get lucky because of product of convolutions, right? So we are interested in the distribution A convolved with itself. In fact, A difference convolution with itself. And whenever you take a convolution of two distributions, in the Fourier domain, the convolution operation is much nicer. In fact, the Fourier coefficients of convolution of two distributions is just a product, NTOS products of the Fourier coefficients. In particular, when you take difference convolution, the new Fourier coefficients are exactly squares of the absolute values of the old coefficients. So they're all, by definition, non-negative. So in particular, A convolved with a difference convolution with itself is not anti-concentrated. Then it is actually taking high values some of the time at least. Okay, if it's not anti-concentrated, then you should also be deviating upwards, not just downward errors. You might wonder why this switch from downward errors to upward errors is useful. Intuitively, it's because we are really looking for kind of a lower bound. We want to say that there is some subspace V on which you have density increment. A lower bound on the value kind of makes sense, and quantitatively everything pans out. So to summarize, spectral positivity says that if you're not anti-concentrated, then I have a lower bound on a K norm for some suitable K. We have to now go from here to actually finding density increment. Okay, so that's the third part. So let's start with the assumption from now on that A convolved with A is taking high values some fraction of the time. Its K norm is 1 plus epsilon. Epsilon is some constant 0.01. And from here, we want to get density increment. Okay. So that's the spectral positivity part, which allows us to go from kind of not anti-concentrated to taking large values some fraction of the time. And now we have to find this additive substructure from this assumption. So recall our goal. The assumption is that A convolved with itself has high K norm. It is taking high values some noticeable fraction of the time. And you want density increment, meaning I want a large affine space where A restricted to it has a constant factor more elements than it started out with. Finding an affine space is a big ask. Affine space has a lot of structure within it. If you think of an affine space, it has like, if I add V to itself, think of subspace even, forget affine nature. Just think of subspaces. So if I add V to itself, I get V back. I add 10 copies of V, I get V back, right? So subspaces have a lot more structure in them. And in the overall question here, we're just asking, okay, find me the subspace directly in one go. But instead of that, we're going to look for something weaker, which has some additive structure, something like a subspace, but something in between. And we're going to find increment not onto a subspace fully, but onto something in between a subspace and a general set called a sum set. Sum set is just any set of the form that any set that can be obtained by adding two other sets. So if I want a large B where A restricted to the sum of B plus B has density increment. Okay. So if I can find a subspace, obviously finding a sum set is easy because I can take V itself. B plus V is V, so everything is fine. Okay, so finding this structure is easier than finding a subspace. Instead of finding the subspace directly, find me something where I have density increment with this weaker constraint. Maybe I can try and do this. And here, let me draw a caricature of the actual argument. I want to describe it abstractly, and then I'll say a few words about what actually happens mathematically. Suppose I have some large set S, it's some subset of F3 to the N, and there's something hidden in there which has nice additive structure, like a subspace, or when I add it to itself, it's not growing too much, and things like that. Is there some operation that I can do to sift out or identify this portion which has this nice additive structure? In this picture, I'm going to cheat and say the structure that I'm trying to identify is this nice square grid here. Is there some operation that I can do which can pick out only the square portion and throw out this other isolated points? And you're trying to sift out, so we actually shift. So you shift your original set and look what kind of overlaps with itself. Now imagine I'm trying to find this square, right? I take a shift along some direction S1. The points in the square are more likely to overlap with themselves. You're isolated, when you shift, you're just going to a random place, nothing happens. But if I have a square, I shift it, it overlaps in a significant fraction with the whole square. Right? Do another shift, something similar happens. The points in the square each time are more likely to survive than those outside. A bigger fraction of the additive substructure would survive than isolated points. If you have a subspace hidden inside, when you take shifts and intersect with themselves, you would expect that portion to survive more often than not. So that's the main idea behind sifting. We were looking for identifying some additive substructure, especially in this form of sumset. So the way we do it is to look at this shifting multiple shifts and intersecting with itself. There's a lot of math that written up here, but at the end of the day, what this is saying is I look at the set shifted multiple times, intersected with all of the shifts. Then I get a set which is almost closed under addition with itself. If I take a uniformly random X from my set B, a uniformly random Y from my set B, then the probability that I end up in my original set is very high. Yeah.
So would you get a larger substructure if you were to take a majority?
Instead of intersection, I think it's very brittle, like your finite fields. We don't lose that much here. We might get some quantitative improvement, but that's something that we haven't considered. So you get some set on which is closed, almost closed under addition with itself. So it is like a subspace property that we are shooting for. Right. So this is the main sifting lemma, which says that look at all points where my density was giving too high a value. There should be many of them because my k norm is big. That's the assumption that we started out with. Then if I apply the sifting operation on it, you get a set B, which is not too small. And B added with itself is almost entirely contained within my set S. That is, when I look at S restricted to B plus B, you get density.
Is this S contained in A?
Not quite. So basically, you have to do another averaging argument where, since it's only a convolution of A with itself, you can condition one of these convolutions, and that gives an affine shift instead of an actual subspace. But you're right, I'm hiding something there. You're actually only finding density increment of S onto a subset, but that implies density increment of A onto a subset. All right. Okay, so we found a correlated subset, meaning you found some density increment. But what do we do with it? We wanted a subspace, right? Subspace is a much more complicated thing. Let me skip this. There's an identity behind why the sifting operation works. I can tell you more about it. It's a little bit like a probabilistic method or first moment method analysis. But the intuition is that when you shift and intersect with itself, a subspace is more likely to survive these trials than random points inside. Okay. So how do we go from subsets to subspaces? Fortunately for us, this has already been done in many other works. It's also called almost periodicity in other works. We use a specific lemma called Zander's invariance lemma from one of the earlier papers, which says that if you get density increment onto a subset, then in fact, you should get density increment also onto a subspace. No questions asked. This is a generic statement which says that as long as for any function, any set S, if B plus B is close to the set S, then there's also a subspace onto which you have density increment. The codimension loses a little bit, but again, as I said, I'm not stressing the parameters. Everything works out as it should. We put the two together, our sifting operation and the known almost periodicity or invariance lemmas. You get the following result that we were shooting for. If A convolved with itself has k norm high, it's taking two high values some fraction of the time. Its value is 1.01 some fraction of the time. Then there is an affine space onto which you get a constant factor density increment. And the codimension is only polylogarithmic, which is what we wanted. So the big improvement is that in Roth's original argument, you had to go to codimension 1 over the density to get a constant factor increment. But now you're getting only with polylog. Okay, so there's a k, there's a log. You put everything together, you get some bumps. To summarize the proof, in reverse order, you have the sifting operation, which tells you that if A convolved with itself is taking high values, some fraction of the time, then you immediately get the other side of the win situation, which is density increment onto a subspace with small codimension. The spectral positivity lemma connects this notion, the assumption that you're using here, to not being anti-concentrated, which was just saying that you're not taking too small values too often. And finally, the third piece is just that if you're not anti-concentrated, then you must have many 3A. So you put all of these three together, you get the result for finite fields with the right parameters that I stated at the beginning. Going from finite fields to integers is not something that I'm going to even touch upon today, but it involves many key technical issues that show up, but uses similar ideas. You have to use spectral positivity again, you have to use sifting, but you have to work with more general distributions. You have to work with something called Bohr sets. At least let me just say what the fundamental challenge is. The fundamental challenge is you cannot do induction so nicely over integers. For finite fields, we said we found density increment on the subspace, and subspace are all the same. It's as if you're starting with the same problem again. Whereas in integers, you find something, maybe even if you found, unless you found an actual progression onto which you have a density increment, you're not with the same problem. So you have to keep track of everything from the beginning. But fortunately, there are some standard techniques to do that. And we had trouble, but Bloom and Sisask have since found a more cleaner argument to do that, which leads us to the main theorem over integers. That any set of integers which has at least delta times any n many elements must have 3-term arithmetic progressions. So that's all I want to say about the proof and our result. Let me finish by stating new techniques. Getting any improvements for the existing bounds on 4-term arithmetic progressions would be very interesting. And finally, let me state a question which is related to 3-term arithmetic progressions, but actually also has applications to communication complexity. And it asks for a question like what we started out with, but now we're looking at subsets of pairs of numbers. So earlier, we just had a subset of integers. Now I have a subset of pairs of integers from 1 through n, and the density is still delta. The question is, how small can this density be, while guaranteeing that your set has a corner inside it? Corner just means that I have 3 points where 3 points A, C, and B, where A minus C, the length of it along the x-axis is exactly the length of B minus C along the y-axis. So you need to find 3 points of the form x comma y, some shift along the x gives you another point. The same shift along the y coordinate gives you another point. Okay. And Behrend's example also shows that there exist corner-free sets whose density is 2 to the minus square root log n. And getting such results like what we have for corners would be very, very interesting, even over finite fields. That's not something that we have. Okay, so with that, let me end.
Hey, thanks, Raghu, for a great talk. We certainly have time for questions. Let me urge anybody online. There were about 40 of you. If you have any questions, please type it out and they can answer it. Not people here. Well, anyone types questions. Yeah, go ahead.
Just a very basic question about your one of the slides about the graph. With the graph, it showed a density function, right? So if the field is small enough, shouldn't it be when you choose randomly points, shouldn't it be very symmetric so there's not going to be any change? If it's integer, I understand.
So let me see.
Can you repeat the question?
Yeah. The question was, should this plot be symmetric somehow?
Yes.
Well, I'm just drawing the, I don't know. So let me just say that here, the x-axis is meant to be the multidimensional space of the entire finite field. And the y-axis is just the probability that particular element appears, scaled by, scaled so that the normalization should be 1. If you're uniform, you're always 1. Whereas, if you don't put any other constraint, your density can take any values as long as its expectation is 1. Right? And spectral positivity puts some constraints on what you can get, but without that, your density could be any function here. The only condition would be that its integral should be 1, or its expectation under the uniform distribution here should be 1.
Okay, there's one question online, which is, what do you think is the tight answer? That is, how close to Behrend's bound do you think you can get? Which is also related to a question I had, which is that if you had this optimal Sanders lemma, can you push it close to half?
Close to half would be difficult, I think. So there are 2 places where we lose. One is, even our finite fields, we only get logN to the 9. So you lose something in Sanders lemma, and also you lose something because let me show you one place where that actually shows up. Yeah, here. So you could think of improving this power 4, but even if you improve that, I think you'd get something like you have a k is again bound to be log. So you get log squared, but then right now we're also doing 1 more log because this is only constant factor increment. So to get a contradiction, you have to repeat it multiple times or find some way to not do it multiple times. You could do it for Roth's argument, but presumably if you do at least the right Sanders bound, you might get like logN to the 1/3. Maybe from there going to square root logN would not be as hard.
I guess it's still the first part. What do you think is the tight answer?
I think square root logN should be the right answer if there's justice.
Yeah. Okay, thanks.
Just want to know if this technique has some implication on algorithms for finding three-term arithmetic progressions. Like given n integers, can you find some 3AP in n square over 2 to log n to epsilon time? Just speculating.
Good question. Sure, actually, I mean, for the most part, like there's one critical ingredient where we use just a probabilistic method kind of argument where you just get existence. So you can say, okay, you pick a random element, then you find an arithmetic progression. That's the easy case. Otherwise, you have to go through the sifting operation. And there it's a little bit existential in our current argument. We just say there is some shift which finds you the set that you're looking for.
Can you find it with good probability?
I mean, maybe, I'm not 100% sure, because it's like a first moment method argument. It just tells you that there should be some S, but good will not still be very good, I think. It will still be quasi-polynomially small, so maybe that's okay, I don't know.
Thanks.
I think it's worth thinking about.
Another question, I'll take the online one if it's okay. I'll come back to you. There are 2 online ones. Okay, so Parikshit asks, what do we know about distributions with all positive Fourier spectrum? Are they all convolutions?
That's a good question. I doubt it. I would suspect not. You can cook up strange distributions by rescaling things, I think. So, not clear.
So that's maybe one more online.
Very good
come back to this. Yeah. Is there a simple, Kunal asks, is there a simple intuition for why spectral positivity lets you translate for anti-concentration from anti-concentration to high density?
Actually, I mean, I stated it in a more general way. I mean, in a less general way than it is true. To demystify it, for any random variable, what we actually use is the following. We have any random variable, all of whose odd central moments are non-negative. If all of its odd central moments are non-negative, then you have this property. X is such that all of its odd moments, once you take out the mean, are non-negative. It is not doesn't have to be true for most random variables. But if this is true, then if you have lower deviations, you also get upward deviations. And spectral positivity is one immediate way to guarantee this, because when you take odd central moments, the constant goes away in the center, and then everything else is non-negative. You do some arithmetic, and everything works out very well.
Thank you. Earlier in the talk, you briefly mentioned that sharpening the density bounds for the existence of three progressions had motivations in communication complexity. And I was just wondering if you could talk a bit more about that.
Sure. So it relates to this corners problem. And okay. So the connection is from an upper bound. If you have a 3 AP free set, then you can use it to solve the following communication problem in some non-trivial way. So what's the communication problem? There are 3 players who each get a number from 1 through n written on their forehead. So there's Alice, Bob, and Charlie. Alice can see the 2 numbers written on top of Bob and Charlie, and then the same thing for the other people. And they're just checking that they want to do a sum check, which is, okay, is the sum of the 3 numbers n over 2? Everyone is getting number from 1 through capital N, an integer, and they want to know if they add up to something which is exactly capital N over 2. So that's the communication problem, nothing to do with APs, right? The trivial protocol is, of course, for Alice to shout out, let's say, Bob's number, and then Charlie knows, and then Bob knows everything, and they can just finish the computation. This takes log of capital N many bits, because you have to write down the entire number. Behrend's example gives you a protocol with square root log n communication. And that's the best protocol we know. And lower bounds wise, we know that any protocol must take like log capital N many bits. So there's this gap, log n versus square root log n. And if you had better AP free sets, then you could get better protocols. So at least this work says that you cannot get substantially better protocols using this approach. The general question of lower bounding protocols is open.
Okay, I don't see any other questions online, and since anyway we plan to. Oh,
do I need a mic?
Raghu can repeat the question.
Okay. Yeah, I just sort of had 2 bigger picture questions. One is, so you mentioned the 4-term case. I mean, can you say anything about, the k-term case as k goes to the infinity? Is the answer to that known? And also, I'm know a bit about van der Waerden numbers, and Green has this result about how long a 3 progression can go without. How do you relate what you're doing to van der Waerden numbers, and is there any cross?
You mean like van der Waerden theorem, or?
Yeah, and so van der Waerden's theorem is 2-sided. Either the integers that are included have a 3-term, or the complement has a 3-term, but you're looking at only one side. So I'm just wondering, is there any crossover?
I'm not entirely sure exactly the thing that you're talking about, but there's a coloring version of the same thing where you don't just ask for 3 APs when you have a small, when you have a large set. But let's say I ask, can you color the numbers from 1 through n with few colors, so that at least one of the colors has a 3 AP. So there are 3 numbers which have the same color and are in sequence. So typically going from density to coloring version is almost the same. There's some loss. You lose the logarithmic bound, which would have been bad for the earlier bounds, but with, at least with this 2 to the minus log n to the 0.09, it doesn't affect the final. At least in that context, it's the same, but I'm not sure of the exact thing that you maybe chat out afterward.
Okay, let's maybe take further questions offline. And as I said, Raghu will stick around for sort of a deep dive into any technical questions you might have. So thanks again, Raghu, for an awesome talk.